In this video, we're going to look at a lot of various integral formulas, not all of them. That would be an insane amount of material. And then see how to apply them in some definite integrals. So first, just a big old list of integral formulas, and they're all based on the derivative forms. Again, this is the antiderivative that we're looking for. So some are a little bit tricky, especially when you start confusing the two, but here's a list of some that show up very often. So we have the antiderivative of a power function. This one does not hold when n is equal to -1 because then I would be dividing by 0. There's a different formula for that that's going to show up later on this list. The antiderivative of sine is negative cosine, and this is confusing for some and causes some issues because the derivative of sine is positive cosine, but the antiderivative of sine is negative cosine. So just keeping that straight can be a little bit tricky. Antiderivative of cosine is positive sine, similar issue. And now again to some of these where we have this antiderivative of secant squared is tangent. And again, that's because the derivative of tangent is secant squared. But when we start getting these squareds, people start getting confused and mixing it all up. Antiderivative of cosecant squared is negative cotangent. Antiderivative of secant tangent is secant. Antiderivative of cosecant cotangent is negative cosecant. And now, if n is -1, that means x to the negative first is the same thing as 1 over x. That antiderivative is natural log of the absolute value of x plus c. Now, a brief piece of information about this before it just sort of disappears. Why the absolute value? Well, we recall that the derivative with respect to x of the natural log of x is 1 over x. But for all of this, we're only considering x is bigger than 0 because that's the only domain, that's the domain of natural log. In here, I want to find the antiderivative of this 1 over x, which has a domain x not equal to 0. And so just the natural log of x is not good enough because I'll get all of the right-hand side. I'll get, everything over here. But I'm missing all of this material over here. I'm missing information. The other piece of information that says it's true is the natural log of the absolute value of x is really just a piecewise function of the natural log of x when x is positive, and the natural log of negative x when x is negative. And if I take this derivative, I get 1 over x. And if I take this derivative, so let me just put a little arrow, I get 1 over negative x times -1. So I need to have something in here to account for the additional domain of 1 over x as opposed to just natural log. And this is the correct thing to do because when I'm in the negative, on the negative x values, or part of negative x values, the chain rule will fix us off, and -1 over x times -1 is still just 1 over x. So that's why this absolute value shows up. Alright, the antiderivative of e to the x is e to the x. So that's one of the easiest ones to deal with. So here is not a comprehensive, but a very useful, workable list of integrals that should be instantaneous to know. Let's see an example of using this. So I want to evaluate the integral from 0 to pi of sine of x dx. And using the second fundamental theorem of calculus, I first find the antiderivative, which is negative cosine of x. And I evaluate this from 0 to pi. I substitute in pi, so I get negative cosine of pi, minus, substitute in 0, negative cosine of 0, I said a theta, 0. This negative minus negative means plus. Cosine of pi is -1, so I have negative, -1. Cosine of 0 is 1, and negative is positive. I get 2, which should be actually a little bit surprising. So I have this transcendental function right here, this very not nicely valued function goes to pi's and such, but the area from here to here is actually equal to exactly 2, a very nice value. So that should be surprising. Second example. Now, I don't usually write my integrals like this, but it's worth knowing that they can be. So this is the integral from e to the 5th to e of dt over t, which is the same thing as the integral from e to the 5th to e of 1 over t dt. So this is the way I usually write them and think of them, but it can show up this way, so don't be thrown off by that. We just talked about the antiderivative of 1 over t is the natural log of the absolute value of t. I had to evaluate this from e to the 5th to e. Now it's worth noting, just because I have this absolute value, things will break down if I cross over 0. If this were a negative here, which means I would go from a negative value to a positive value, because of how this function looks and how these end up approaching positive infinity and negative infinity, it actually breaks down. But since I'm always positive, that works out well. So I'll do natural log of e minus natural log of e to the 5th. I don't need to maintain the absolute values because e is positive, e to the 5th is positive. Natural log of e is 1. Natural log of e to the 5th is 5 because natural log and a power of e are inverses. And I get negative 4. Final example, and this is just to show that it's definitely not a list that covers everything. We know this antiderivative, but it's not on the list. And there are other things that can show up that we may not know the antiderivative, but we can still evaluate the integral. So don't think that if you memorize that, you're done. I need to recall that 1 over 1 plus r squared is the derivative of arctangent. So I'm going to do the inverse tangent evaluated from negative 1 to 1. And so I find the inverse tan of 1 minus the inverse tan of negative 1. And it's actually not too hard. We have the unit circle. I'm going to refer to this. Tangent is 1 where the sine and cosine, or the y and x values, are equal. That happens here at pi over 4 and here at 5 pi over 4. The arctan function only has these values in its domain, so this will be pi over 4. Arctan of negative 1, well, the tangent is equal to negative 1, where sine and cosine have the same magnitude but opposite signs. So over here, the sine is positive, the cosine is negative. This is at 3 pi over 4. Over here, the cosine is positive, the sine is negative. That is 7 pi over 4. But there's one additional problem. These are both on the unit circle, but they're not in the domain of arctangent. Arctangent is sort of this continuous region through here, including 0. So I actually need to go back to the coterminal angle, and 7 pi over 4 is coterminal to negative pi over 4. If I take 2 pi away, and then I subtract them, pi over 4 minus negative pi over 4, well that's plus, so I get 2 pi over 4, which is pi over 2. I hope this helped out. Feel free to comment below if you do have any questions.